No gentlemen. Oh, and gentlemen, sorry. Good morning, ladies, and a gentleman. And thank you for coming. I'm Martin Dyster. I'm the Vice President of Business Development and Project Director of the Telos Infinity Intercom system. And I'm going to be talking to you today about how we used SMPTE 2110-30 to reinvent broadcast intercom. I'm going to start with a short history lesson going back in time to year zero for audio over IP, and a little look at what our lives looked like before audio over IP became a reality for most of us. So in 2003, this is a picture of me in the midst of an installation somewhere in the world, working as a systems integrator, covered in cable, trying to find out why there's a phase error or something along those lines. And that's what systems integration used to look like when we had to run a balanced audio pair to every single connection before we had audio over IP and any kind of streaming. We did have MADI, I suppose, but in this particular instance, we didn't. So this is a follow-up for an installation I actually worked on in Lisbon, in Portugal. And this is a good example of the tens of thousands of connections that we used to have to make to make an audio system work. We used to have routers that are hundreds and hundreds of ports. Every single one of those ports had to be distributed. Every one of those distributions had to go to a patch field, and before audio over IP, system design work and installation was an absolute nightmare. Kept wiremen employed and made people at Belden very, very rich indeed, but it was an entirely different world from the world that we live in today with IP audio. And here's some schematics. You can see all these pieces of equipment in there that quite frankly aren't needed anymore. Distribution amplifiers, for example, dedicated routers, that kind of thing. If you use a distributed audio system as AES 67 and SMPTE 2110-30 is designed to do, then a lot of these pieces just melt away into the background, and your switch fabric becomes your router. So 2003, I picked that year for a reason. 2003 was the year that the Telos Alliance, the company I worked for, introduced Livewire. It was the very first audio over IP protocol, and it became the predecessor of AES 67. So 2003 was year zero for audio over IP. Shortly followed by, in 2004, the very first installation at Auburn University in Alabama, the first station or the first broadcast facility to become an all-IP installation. In 2006, our friends at Ordinate in Australia introduced Dante, and I'm sure everybody's aware of the success story that they've made of that protocol. And Wheatstone invented or brought out WheatNet in 08. 2010, our friends across the way there at ALC Networks brought out the Ravenna protocol. And what you can take from this is in that 7 years, and these are only a few of the protocols that came out, we started to get a surge in proprietary protocols which needed to be addressed. The AES formed the X192 working group to start looking at protocols in 2010 and trying to figure out if there was a route towards an interoperability standard. And as a result, 3 years later, the AES 67 standard was born. So, with AES 67, we needed to move that forward. We needed to work on interoperability standards, and the Media Network Alliance took on that mantle to encourage manufacturers using protocols like Ravenna, like Dante, and like Livewire and others to test their products and make sure everything worked together. Moving forward, AIMS, the organization that has brought us all together at this part of the AES show, formed in 2015, and then ultimately get to where we are today, 2017. Obviously today's not 2017, but 2017 was when SMPTE 2110 was the Dash 30 was born, using AES 67 in a slightly adapted form to become the audio over IP standard for media over IP. The reason that we're sat here in this little part of the AES show. So audio over IP has many trade-offs. Many payoffs. Not least of all, because it moves us forward from those kind of over-complex systems that we used to build everything around baseband using. It's standards-based. It works on a layer 3 switch fabric, as I'm sure most of you know. It's standards-based. It uses switch multicast to get rid of all those, get rid of centralized routing, or it should do anyway. If products are designed that way, distribution amplifiers, patch bays are pretty much a thing of the past. I used to design systems for a living. I could not find a broadcaster who would dispense with a patch bay back in the day, as strange as it seemed to be able to patch around everything as a backup was ubiquitous at that time, and now there's pretty much no need for it. Cabling's reduced, rack space is reduced, weight in OB vehicles, and system design is less complex. So audio over IP helps us in many ways. And audio over IP is ubiquitous now on many of the products that you'll see walking around this hall. But intercom hasn't necessarily moved on. Intercom systems, as we know it, still tend to look a little bit like that. They still tend to use a centralized matrix of some sort, and our feeling from, I'm just looking at my friend from Riedel over the back there. He's going to start throwing things at me soon, but no, the reality of it is that with the way that we communicate every day, at the Telos Alliance, we looked at the way intercom works and figured out that actually we don't need those matrices. We don't need a matrix-based intercom anymore. Something we should be moving away from, and that doesn't necessarily seem to be happening, but it was the mantle that we took on. Well, the matrices can be a very practical thing. There's lots of reasons for using a matrix, not least of all because it's reliable, it's familiar. Cross-point switching is achieved using a matrix. It's easy to create party lines, IFBs, and groups and things like that. All of those pieces that we're familiar with in comms are easy to do using a matrix. So there are reasons why the technology has not really moved forward. It's a known commodity as well. People seem to be happy with intercom working that way, but there are some negatives as well. There's a lack of flexibility. For example, you are bound by a port count. There's a point in a system design where you have to sit down with a spreadsheet and you figure out how many panels do I need, how many 4 wires, how many telephone circuits, and you come up with a number, and you buy a matrix that's based that's maybe 10% bigger than what you know you need, and that becomes a limiting factor. Channels are handled by bus structure. It means there's a finite amount of processing that can go on inside a matrix. It can be expensive and prohibitively expensive to trunk multiple frames together if you need to do that, depending on the brand that you're looking at. They take up rack space, of course, and some of the larger products from some of the well-known manufacturers take up an awful lot of space. And ultimately, the one thing that is true is everything cables back to that central matrix. Even if you're using audio over IP, those connections have to make it back to the frame. And that frame, by definition, becomes a single point of failure. If you lose the intercom matrix, you lose all your comms. So with all that said, our challenge that we put to ourselves was to build a matrixless intercom system that did all the things that a matrix-based system can do. So we started with a constitution, as all great things do, and we wrote a few things down. Okay, we're going to build a system with absolutely no matrix. Everything's going to be distributed. All DSP is distributed, meaning that the devices that sit on the network, the panels, belt packs, other devices that are part of the intercom system that add to our world, which is a kind of distributed virtualized matrix, have DSP on board. We needed to produce products that are familiar in software and hardware terms. Intercom users need a microphone, they need buttons to press, they need speakers to listen to, and they need displays that are clear and tell them which button to press to talk to somebody. Pretty obvious stuff. So, you know, we're reinventing intercom, but we're not reinventing the wheel. We wanted a product that would meet or exceed customers' expectations. We're starting from a blank sheet of paper here, but there are certain features that that you absolutely have to have. We wanted everything to be standards-based. That was one of the most important factors about the product. It had to be standards-based, so we used AES 67 natively. We used VoIP codecs that are known. We used the Opus codec, which is free. And we wanted the product to be a native part of a SMPTE 2110 environment, a SMPTE 2110 ecosystem. So any products that you may look at, or you may have looked at in the NAB New York hall over there, that are SMPTE 21 compliant and move audio around, can work natively with an Infinity system without the need for additional connectivity. If the streams are on the network, we can pick the streams up, we can use them as part of the comm system. Scalability, we talked about the restrictions that you have in a matrix size. We don't have those restrictions with a network system. If you've got a port on your network, you can add a device, you can make your intercom bigger. And resilience, of course, as well, both power and data. And we also recognize with customers we talk to, that some people find incumbent intercom systems complex to program. There are too many layers in the menu structure, so we wanted to create a UI that simplifies all of that, that debunks all the myths about the idea that maybe there's only one guy in the shop that can actually program the intercom system, you know, and if that expert's off for the day, there's nobody who can go near it to make changes. But we wanted it to be easy to use for people at all skill levels, and hide the complexity under the hood as well. So that everything it does, the secret sauce inside the Infinity system, is not something you need to worry about. It just does its job, it's reliable, and you can communicate. And also having a blank sheet of paper to work from meant that we can think outside the box. Terrible cliche, but you know, that's the reality of it. We can do things with IP that can't be done without it. So, this introducing the Telos Infinity intercom system to you. It's all new. We designed it from scratch. It is standards-based, and we hit all these markers that we set out to achieve when we designed the system. It's standards-based. It is entirely matrix-free. It's fully featured, infinitely scalable within the boundaries of your ability to design a network that can cope with thousands of signals. We believe that's a lower entry into the market and maintain costs by not having a matrix to pay for, and it seamlessly integrates with voice over IP using the Opus codec. Okay, so having a little look under the hood at how Infinity really works. So this is a simplified system design that shows you at the top, it's clipped off a little bit, but it shows you what an Infinity device looks like internally. If that's an intercom panel or a belt pack, it doesn't really matter. That's broadly the way it works. We start with the baseband interfaces. So an intercom panel obviously needs a microphone of some sort. So on the left-hand side, you can see the A to D converter bringing audio into the system that's converted to audio over IP. And on the output, also a baseband interface, a D to A converter to drive loudspeakers or headset. On board, we talked about DSP. We have a huge amount of DSP available on a panel or a belt pack. So we have, those are divided up into small mix engines. These are the things that allow you to create conferences, the things that allow you to create IFBs within the Infinity system, or to create groups, or for a panel operator to listen to multiple sources at the same time. We also have a bank of AES 67 transmitter receivers that work with the mix engines to allow the system to communicate and allow you to build a bigger system. You need to have an embedded UI so that you can program the product, and every device has its own built-in web server. So you can simply browse onto a panel and adjust mic gain, adjust brightness, all of those things that you need to do day-to-day operation with an intercom system. And also physical UI, buttons, knobs, things to press, keys to talk to people with. That I think goes without saying. So the way that the system is programmed is using a device called a software device called Dashboard, which runs on a server. It analyzes the network, it discovers all the devices, and it creates a user interface on screen that looks and feels like an intercom system. It's our configuration tool. It can discover AES 67 streams on the network, it can discover devices, and it compiles them into a UI that's easy to use, using drag and drop, and very, very simple, no multiple layers of menus to wade through. Everything that you see on the intercom system is available on the screen in front of you. Using third-party connectivity, we use our own Livewire protocol. We're working through NMOS at the moment, Ravenna, SAP for connectivity to Dante. That's all natively on board the Infinity system, so that means in an environment using SMPTE 2110 or AES 67 formats, you can connect to anything that you need to connect to. You don't need a separate interface. You can discover and connect to audio streams from third-party devices, and you can connect to them going back the other way. So maybe you're bringing mix minuses in from a Yamaha console, or you're sending audio out to a Dante IFB device. You don't need to buy a separate card. You don't need a separate license. That's on the network, and you can connect. And then our own devices, for example, products like X nodes, which are our baseband to IP converters, our 4-wire devices, if you like, or our telephony products like the VX. Over on the right-hand side there, they're natively discovered and natively managed by the intercom system. So we have options for connecting to AES analog, mics, VoIP codecs, our own mixing consoles, anything within the Telos Alliance, Axia and Telos brand. Okay, so how does it really work if I do something simple like create an IFB? Obviously we don't have a matrix. We have our software managing the system, at least during programming. We have a very simple system on the screen there where we've got a couple of panels, our LAN connectivity, and our talent down in the bottom right-hand corner, who's connected using an IFB fed out from one of our X nodes as an analog source. So I create the notion of an IFB within the software, and that little green dot appears. That's the notion of an IFB. And when I do that, what will happen is the dashboard software will assign a primary and a secondary mix engine. I've only got 2 panels shown here, so there's one on each panel. I'll add a source to that IFB, that source coming off the mixing console. In this case, I've shown a Calrec, so let's say that's an AES 67 stream coming from that Calrec Brio console. It's subscribed to the primary and secondary mix engines. That audio is then routed out to the destination in this case being the X node, which is then presented to the talent's earpiece. The destination subscribes to the primary multicast address, and that mix minus, as I say, is created and sent out to the talent. So now I need to add buttons onto the panels to talk to the IFB, so that those two, the director and the producer, can talk over the mix minus to the talent. When they press the button, they literally duck the equivalent fader in the DSP core, and they talk over the mix minus to the talent. So that's a very simplistic look at how we create things like IFBs or party lines or groups within an Infinity system where there's connectivity to an external stream like an analog IFB. Okay, so another look at a typical installation. This is taken from a real Infinity install, just to show how simple the system can be. The kind of candy stripe in the middle is our network infrastructure. In this particular case, I know the customer's using Cisco switches. Their panels are connected to the Cisco switches, and all their other elements of the system. Camera CCUs are connected via analog converters. The wireless system, in this case, they bought a CrewCom system from us, again connected as analog 4 wires. And the mixing console, I think it was a Wheatstone, but I've used a Calrec on there, and again that was connected using analog converters. And then the wide area network connection to several outside locations, a remote office, and also to their news gathering SNG was using our Infinity Link Opus codec product, which is natively on board the devices that exist in the truck and the panels in the remote site. So that, although it's very simple, isn't far off the actual system diagram that was used to put it together. And if you compare that to a typical system schematic of a matrix-based intercom system of old, then it's very, very different indeed. So if customers have multiple studios, then it's a step and repeat function in terms of design. More switches connected to more panels, and the infrastructure can grow organically from there. Our Infinity Link product, that blue cloud is the internet in this particular case. As I say, uses the Opus codec and is available in different product forms. It's available as a dedicated gateway device, a 1U package form. It's also available on the panels themselves, on the belt packs themselves. You can activate the codec directly onto our devices and connect those to the internet to expand your system beyond the boundaries of your local area network. Okay, so that's my wrap up for a little introduction into the Infinity system and how we used AES-67 to create a matrix-free intercom system, and how that was turned into a reality. 25 minutes, that's not bad. Any questions from anybody at all? Aha, questions. Let me move. So the question was, what happens if two people talk to an IFB at the same time? So on that slide that I had back there, if both panels talk at the same time to the same IFB, then the two panels will, their outputs will mix through the mix engine, mix together into a single stream, which is then centers a multicast stream out to the IFB. You have no real restriction the number of people that can talk at any one time, apart from the intelligibility of it. But if 5 people talk at the same time, they're mixed together in the mix engine and they're outputted to the IFB. So that's how that works. Any more for any more? I should say we have an Infinity system on the display over there at the end of the pavilion. So please come and talk if you want to learn more. Thanks.